Assembly Language Tutorials, Chapter 6, Section 3. In the previous video, we talked about various shape and forms of jumps, which are equivalent of the if statement used in other programming languages, the higher languages like C++, Python. So in this video, we'll talk about various shape and forms of loop instructions. There are quite a few. So even they work on the values of the flags, especially the zero flag. That's the only flag we care about when working with different types of loop instructions. It's quite simple. By the way, it's so simple that we do not need much slide over here, and we just have a demo. This video would be a real quick one. There are 4 types. So loop Z is if the zero flag is set to 1, so it's loop Z, and loop E is same as loop Z, so the opposite would be not equals to 1. If the zero flag is not equals to 1, so it would be loop NZ. Now what is a zero flag? So we have discussed in detail about the 20 types of flags out of the 32 bits of all the bits in the if flags register. We have like dissected that bit by bit. So out of those 20 bits, only 5 are relevant to us: overflow, carry, parity, auxiliary carry, and the zero flag. So zero flag happens when a certain assembly instruction changes the destination value to 0. That we know. So if you don't know, I'm reiterating that so that to refresh your memory, and to know more about flags, you have to go back and watch previous videos. In the second video, x86-64 architecture, we have covered all the flags, and in the previous video prior to this one, so we have covered all the flag values and how each jump instruction takes advantage of that. So let's see a demo for the loop instruction, how it is useful. So here is my demo, and this source code would be available in GitHub. Link would be provided in the description section. So here is a contiguous memory location, our good old array. So it's a num, so it's of byte type, and there are around 1 2 3 4 5 6 7 8 elements. And here is our another variable which is of undeclared type. So here I am clearing out the ESI register because I have to loop through the instructions, so loop through the array. So what's happening is here we are using the loop Z. So let's talk about this before we get into this. So here I'm clearing ESI register, and because I'm using a loop instruction, so we know that we have to use the ECX register, which is the internal loop counter. So I need to set a value for ECX, so that I got from the length of directive. Now all these have been covered in previous videos, so I will not explain that over here. So it gets the number of elements inside this array. Actually, calling it array is a misnomer. Let's call it contiguous memory location. That would be big one. So let's call it container. So in the nums container, we know the length of all the items there, so we store it into ECX. Now we have the ECX, so we can use the loop instruction, and inside loop iteration this ECX would be decremented. That's the whole point. Now XOR EX, we are clearing out EX because down here we are using the AL register, which is the lowest byte of ECX register. Now here is our label, and our first instruction inside that label is move AL nums ESI. So here this square bracket is a dereference. Now ESI is 0, so nums 0 would be pointing to the first element. Now we are doing something like C++, accessing an array. It's very similar. And then I'm incrementing that ESI add type of nums. Now type gives the, which is of, if it is byte type, then it will give 1. If it is dword type, it will give 4, because dword is a 4 byte. So even we have covered this type instruction as well in the second video, so you should go back and check that if you have further doubts. So I'm incrementing ASI, and then what will happen is while the loop is running, so next time the next time this instruction is run, so it will be ASI plus 1, and then next ASI plus 2, 3, 4, and so on. So these are like our fetch kind of instruction. And here is our test. So test, we know that it is an ANDing operation with this guy over here. Now 01H, so it would be in binary and it would be ANDed with AL. So AL, now we have a calculator. See, calculator is useful. I talked about it. So the 2 over here in decimal 2, we have a binary of 0010, and then 1H. So 1H would be, it would be 1 only, so 0001, right? So what's happening is, let me put a comment there. So and 0010 010, it's in binary, and hex is 1, so 0001 1. So now what's going to happen is, now these are these bits are not set, only this bit is set and this bit is set, so it would eventually become 0000. Pretty straightforward, isn't it? So if it is 0, now this, what it would do, it would set the 0 flag to 1, because this assembly instruction, it's actually checking that okay, this destination now is 0, because this is not an implicit AND, because test doesn't modify the destination. Had it been a real AND, something like this, the AL register would be actually modified. So now it wouldn't be modified, only the 0 flag would be set. Let's see that. Debug it. Okay, so our EAX has 2. Now this is our 0 flag, and sure enough we have our 0 flag set. So in the next time when it comes over here, it would be some value, and then the ANDing would happen to that. So again it would keep looping through that. So as you can see over here, there is a pattern, like all these numbers are even and only this guy is odd. So I have a table here. So if you can see this table, like all these odd numbers starting from 1, so you see that the last bit for all the odd numbers is set to 1. See, there is a pattern over there. So it means is, while we are doing this AH, which is nothing but this guy over here, so it would make sure that all these numbers, it would make sure that all these numbers, whether they have really the last bit set to 1 or not. That's what we are checking over here. So if the last bit is set to 1, that number is odd. So based on the 0 flag, we can know that we have encountered an odd instruction. So we have loop Z. So the 0 flag is 1. When 0 flag comes, we would know that this value is a odd number. So that's what we are doing. So let's step through it. So it keeps changing, loop is still running, loop Z, and now we are out of the loop. Our execution is over here. So the last number we had in EAX register is 07, which is the first odd number. After that, this test would have had happened, and let's see what's the value of 7. 7 in decimal binary is 0111. 0111. So it means it would be 1. So the 0 flag, so this is not 1, so the 0 flag is not set. because if it would be 0 it would be set to 1. So our condition is validated over here. So now we know that the 0 flag is not set. It's time to come out of the loop, and now we can move the value stored in the AL register into res. So you see over here it's empty. Now I will step through it. Let me pause this. Let's run one more time. And sure enough, our value is 7. So let's test this one more. Let's change these values. Let's make it 1, 3, 7, 9. Let's keep it even. Let's make it 11, 13, 3. So now this loop z, now we have to loop nz, because now we are checking the even number. When the even number comes, our loop should stop. So our 0 flag would be not equals to 1. So let's see what we get now. We should get this number 8. Step through it, and sure enough we got this number. So I hope it makes sense. And these flags, we have to deal with flags all the time. This flags register is super important. I can't stress enough. It's super important. And all these instructions, these jumps and loops, they always work around flags, all these type of flags. So do more and more hands-on. So this is just my explanation only, but it is by no means it's exhaustive. There are so many scenarios, so many stuff, and we could have so much coverage. Like in loop instruction we saw these variation. In jump there are like 16 type of variation we saw in the previous video. So play around with those things. So unless you have a good grip on these things, because in high level languages you have just if statement and some ending operation there, so you are done with that. But here you have to like manually check everything, each and everything. And when you compile something in the high level languages, so compiler, it takes that source code and converts that into intermediate, sometimes in assembly. So you could see the listing file also, which compiler generates. So it's nothing but the assembly file. If you compile a C program, you can see that. And then that file is eventually converted into an executable file after linking, and the it's converted to object code, and the linker takes that object code and produces the executable file. So there is no magic around here. So everything will make sense eventually as we progress through these videos. So it's very important that do not skip anything. Do not skip anything. Check all the possibilities. Run each and everything. Like if some video doesn't make sense, if you are watching this video and you find some confusion, so go back and watch previous videos again. So I'm trying my best to make it so much accessible and so much easy for anyone who wants to learn assembly language. Otherwise I would have picked up a command line and text editor and some stupid VI editor or something and would have done it there. But I'm doing it in IDE so that to make it as easy as possible. And eventually we will cover Win32 API as well, which I have separate videos on that. So I'm not quite working on them right now. After I finish this assembly, I will jump back to that, and then we'll deal about advanced assembly. We will make use of the Win32 API inside assembly to develop applications. So we could develop freaking application in assembly. So this assembler is a very powerful assembler. You means as you see all the videos. So I have couple of videos, like so many videos coming along. So I will cover them. So you will learn a lot. You could do anything in assembly, like so many stuff. And from security standpoint of view, all the vulnerabilities that we find, name it Spectre or anything, it's just something happening at the machine level. So you have to go down through these instructions. You have to learn assembly, even though the Spectre is more of towards computer architectural level, but at least all the vulnerabilities like use after free and the heap overflow and those things, and bypass mechanisms like control flow guard, ASLR, and everything, it just deals with assembly. So I can't stress enough, assembly is very important. Even today also, even if people ask me this funny question, why the hell we should learn assembly? Unless you are a security folk, you shouldn't give a shit about that. But if you are a security folk, you want to be a researcher and do something, assembly is must. So enough talk, I guess, and I really emphasize that you get a good grip on the jump instruction and the flags. And I catch you guys in the next video. Do not forget to subscribe, put a thumbs up, and post your comments, ask me questions, and have a good day. Bye bye.